So now look at these expressions. Of course, these are not sequences, no? So the headline is sequences and arithmetics. So this is, like I said, sort of a warm-up calculation about fractions. And so, of course, expressions of this sort will very often appear inside certain sequences. So it's important to really be familiar with all the potency laws and transformations by reducing expressions like this. And that's what we do here. So what do I do? Well, my tendency, it's not necessary, but my tendency is if I see different numbers like 4, 9, 2, 3, I always break things down to prime factors. That's a good idea. Okay, it's not, like I said, it's not necessary, but it's always a good idea, because then you get a clear sight about which of these, exponential or whatever potency expressions have common basis, so that you can perform like a reduction. Okay, so what do I have? 4, it's 2 squared, and then here 9, of course, this is 3 squared. So what I do is I put this in the form of firstly a fraction divided by another fraction can be rewritten as fraction times, you know what it is, reciprocal fraction. Okay, so I use the reciprocal of this one and multiply it. That's an common rule. Fraction divided by fraction equals fraction multiplied with the reciprocal fraction. That's what I do. So I pull this 3b upside and then squared. Also, I remove the parentheses so that I have to square the numerator and the numerator and the denominator. In the end, I get 3b in parentheses squared here in the numerator, and in the denominator, I get this expression squared. That's the second part. The first part, of course, like I said, is 2 squared here and 3 squared here, and also x power 3 times y, a squared times b below here. So that's nothing really new. And but also here, I actually applied this exponent of 3 to both components. Okay, to everything above the fraction line and below the fraction line. So now the important step is just to use the 5th law of potency, so that I have 2 squared and then also to the power of 3. You know that this is like the general rule which says that a to the power of b, and then we should use parentheses for clearness, then to the power of c, like something like a combined or a, let's say, recursive exponentiation. Yeah, so this can be rewritten as to be a to the power of b times c. That's what I'm using here all the time. Okay, so I get 2 times 3 is 6, so I have 2 to the 6. Look at this one in black. I get x here, 3 times 3 actually is 9, so I get x to the power of 9, if you can see it in black color here. And then y power 3, this one, everything in black. Below it's 2 times 3, so 3 power 6, a power 6 also, and b power 3. Going on, just putting this together to one fraction. 3 squared times b squared, just removing the parentheses. Then 2 squared is, where is it here? 3 times 2 is 6, so x power 6. Then a power 4 here, and y power 2. That's all. And now I'm shortening or as far as I can. So 2 squared shortened against 2 power 6. Just take the difference. This is actually the 2nd law of potency. 6 minus 2 is 4, so 2 to the power 4 remains. First step, different colors for the different steps, okay, so that you keep clearness here. Let's look at this. 3 squared is contained in 3 power 6. 6 minus 2 is 4 again, so 3 power 4 remains here in the denominator, as you see. Also, this is y squared, y cubed. So crossing out, I keep factor of y here, which is remains, okay? And that was the violet color. Did I forget anything? I don't think so. So everything that remains, actually, I should perhaps circle this one and also this one. The circled expressions remain. The green ones, the blue one, the red one. In the end, it's 2 power 4 x, oh, sorry, I forgot the x term. X power 9, x power 6, 9 minus 6 is 3, so x power 3, x cubed remains in the numerator. So that's it. I should have circled this one also. So then, in the end, it's 2 power 4, x power 3, y, and below it's 3 power 4, a power, look at this, a power 6 times a power 4 means a power 10. Of course, you can add exponents. That's the first law of potency. Okay, so then we have 3 power 4, a power 10 times b, and that's it. Perhaps it's a little disappointing. That's the result. It's just a training on laws of potency. That's all. So similar to, in this respect, similar to the next one, which is meant to, well, to train a little bit the summation of terms in a special form, so that this expression is summed up, you know this, over k, running from 1 to n, but then also afterwards summed up over I running from 1 to m. So take care what you're doing, and remember, well, one of the probably most famous little special formulae, you could say formulas of arithmetics, which actually has been invented by the famous mathematician Gauss when he was a child. And then it's about, so now let's have a look at this one. It's called the Gaussian summation rule. I'm quite sure you know it, or you have encountered it. If not, there's a little example which makes clear why it is, okay? This Gaussian summation rule says that the summation over k running from 1 to n is nothing else than, well, the highest number. Okay, so you know what this is? It's just a sum like 1 plus 2 plus 3 plus 4 and so on plus until plus n. So the highest of these terms is taken times the next number, n plus 1, and then the whole expression is divided by 2. And it has quite an easy reason, and this was, well, this was, you could say, the trick that Gauss used when he was a child to find it out. There's an anecdote which says that the pupils of the class were asked to just take their pencils and sum up all the numbers from 1 to 100. And obviously Gauss found an easy way to do it, and then took him 1 minute and he was done. So let's take a little lower example with lower numbers, which takes the sum of all the first 10 natural numbers starting with 1. So from 1 to 10, which is like 1 plus 2 plus and so on, plus 9 plus 10. Look, what can you do? You can rearrange this, taking the lowest number plus the biggest number, firstly. Okay, so that's like 1 plus 10 in parentheses. And then the next contribution is you take the, how do you say, the second but lowest. Do you say so? I don't know. The second but lowest and the second but biggest number of these. So it's quite the same as here. Lowest plus biggest, but now this time it's 2 plus 9, and look at this. The sum is 11, and again the sum is 11. So adding up pairwise from the outside to the middle makes it much easier, because you always have the same contribution of 11 with each pair. You see? And now you just have to count the pairs, and you find out, since these are 10 different numbers, 10 subsequent numbers, the number of pairs we can build this way or construct is, of course, half of 10, so 5. We have 5 pairs, and each pair has an intermediate sum of 11. So that's easy, and it just means that 5 times 11 is the result. 5 times 11 is 55, of course, and that's it. But now you see that this is much the same as what this formula says. It says, look at this, n half, this is the number of pairs you can construct, and n plus 1 is nothing else than the intermediate contribution of one of these pairs, the single contribution of a pair, like 1 plus 10 in this example. So this is the general form of what we just did, okay? So it's quite nice. So using this, let's put this expression in a simpler form. Now, the first thing is, if you sum up over k, you note immediately that the factor of I is constant regarding this summation. Since it's constant, it means it's not affected by this summation. And this again means that you can put this factor of I outside of this sum, but not, please be careful, not outside of all this. So just in between the two summation signs. That's what you could do. You could say, okay, we still have to sum up over I, but now the expression is called I times this sum just taken over k. You know, this is a factor not affected by this summation, so we can pull it outside of this sum. So that's what I'm doing. And suddenly it looks here, from here to there, it looks like this. And then I can just solve this summation using Gauss's summation rule, which is what we just did. So I replace this one by looking here, k runs from 1 to n, just taking n times n plus 1 divided by 2, the whole quantity divided by 2. And this factor of I just stays there. And then since this is done and not dependent anymore of, just dependent of n, not of I, it's the same thing. We can put this common factor of all these terms inside. Every single contribution of this sum contains the same factor, n times n plus 1/2, and this one can be taken outside this time, outside of the whole summation. What remains is a summation over I, running from 1 to m now. And of course, this is much the same as here, just with different symbols, and I running from 1 to m. So now this time m replaces n from here. So the expression is of the same sort, but not identical to this one. It takes the form m times m plus 1 divided by 2, of course. Okay, since the number of terms we have inside this summation is a different one, then it's called differently than here. So, but in the end, it's just the product of two of these Gaussian terms, like you see here. So also this was like a warm-up training.